Hi everyone, my name is Szymon. I'm a software engineer here, and I'm going to talk about building event-driven state machines in Elixir. Before we get into that, let's think about state for a second. As you all know, Elixir and Erlang are functional languages, and Beam enables developers to run a huge number of lightweight processes that communicate with each other concurrently. Because of that, it is a common practice to run to store a state inside of a process that recurses upon itself and that other processes can communicate with in order to read or modify the state. Another possibility is to use ETS or persistent term, which allows you to have a state that is shared between many processes, and this way you avoid the bottleneck caused by a single process holding state that other processes have to access. But for this, you need to make sure that for the problem you're approaching, there won't be any race conditions when read and write operations are done concurrently. So for most cases, state inside of a process is the approach. So let's go deeper there and think about how can we store and manage state in processes. Of course, you can build everything from scratch, but in most cases you want to use the abstractions that Elixir provides, so GenServer behavior or agent, which is built on top of GenServer. If your problem is specific enough, you may want to look for some third-party solutions, of course. And what may go unnoticed, especially by devs who come to Elixir without former Erlang experience, is that OTP offers more than that. So yeah, this way we've come to the main point of this talk, which is GenStatem. It stands for Generic State Machine, and this is the OTP behavior, which first appeared in OTP 19, and is a successor of GenFSM, which stands for Generic Finite State Machine. The difference between these two is that Generic State Machine provides a more convenient API, and it also brings some new cool features in. Okay, so I rambled on about state machines, but what are they exactly? I won't go into deep scientific definitions. The most straightforward explanation is that state machine is a model of an abstract machine that can be in exact one state at a time out of finite number of all states, and that can be changed only by transition. That is a part of the model. So to picture it better, let's think about vending machine as a state machine. For simplicity, we have 4 states here. So waiting for product selection, waiting for coins, product dispense, giving back change. And these are the transitions. Apart from the most obvious ones, you have transitions like timeout or cancel. Yeah. And now, what is an event-driven state machine? This is a kind of state machine in which transitions are triggered by events. So, it fits our Erlang case where we have state inside of a process and we have messages incoming to this process, which are events. Now, this sounds like something you can do with GenServer. So why another behavior for it? Well, of course, there is nothing you can do in generic state machine that you can't do in GenServer, and the other way around. But for some problems, having it done in generic state machine is just easier. So I'd say if your problem has a natural representation as a state machine, and that this state machine is not really trivial, and that you're going to use features that generic state machine provides, then you might want to consider using generic state machine. If not, then I think you'd be good with sticking with GenServer. Now, what are the features of generic state machine that makes it stand out? Firstly, state is split into state and data. Moreover, a separate event handler function, you can have a separate event handler function for each state. These two features make you focus on our state itself, the type of a state, and you can make your code more readable and organized. An amazing feature of generic state machine are timeouts. You have three types of timeouts here. So state timeout, which is cancelled automatically on state change. There is also an event timeout, which is cancelled automatically by an oncoming event. And there is also a generic timeout, which has no automatic cancellation, but you can cancel it manually with your code. There is also event postponing. So imagine you have an event is incoming, but you want to ignore it for now and handle it in the nearest state change. You can do it with just one line of code in GenStatem. Next, state enter calls, which is an optional feature. When enabled, after each state change, there will be a new event incoming. That is an enter event, and you can run some code on every state change. So imagine, for example, when you have to send a message somewhere, broadcast the state. This is really, really convenient then. And with generic state machine, you can have purely internal events, which means that state machine can emit events to itself. So these are the most important features described briefly. I won't go deep into them because that's what documentation is for. Instead, I'm going to code a sample state machine to showcase its most important features. So we're going to build a battleship game. More specifically, a process that handles a single duel between two players. In case you don't know this game, this is a simple guessing game between two players. When first you have to set up your ships, and then you need to guess the other player's ship placement. So it's pretty simple. Our state machine model for this looks like that. So we're starting with ship setting up states, and when both players are ready, we're transitioning to countdown. The countdown state transitions automatically after some time to the game. And the game is split into two sub-states. So player 1 turn, player 2 turn. And when a player makes a move, then it's another player's turn. And also, when a player doesn't make a move, their state is timed out and the state transition. And also, we have like a big game timeout. In case like no one wins for some time, then we're going to transition automatically to game end. And game end is the last state. Sorry. Okay, let's now try to code this. So as you can see, I have some code written beforehand. So we have some client functions. Like in GenServer, you can do call and cast. And there are some utility functions which are related to game logic, which are not really important. And in callback section, we have just the init callback. So it sets the initial state to setup. and the initial data to two players with ships being an empty map set and ready flag set to false. All right, let's start with implementing the obligatory callback, which is callback mode. There are two callback modes in generic state machine. The first one is state functions. For this mode, each state will have a single handler function you can use. So you will have, for each state, you will have another separate function. And there is also handler event function, which works that way that you have a single handler for every state. So let's start with separate state function. Okay. Now we can do something like that. So we are in state setup. So we're doing this, and we can handle the oncoming events. So let's handle the place ship event, which is call. There is the second argument is event data. So place ship player position, and the third argument is data. Okay, let's now place the ship. So I'm going to use the helper function I made. And the return value of a handler function is a tuple. And the first element of tuple is an atom telling what we are going to do with state and data. So in this case, we're going to keep state, but we're going to modify data. And the last element of tuple is our actions we are going to make. So in this case, we're going to reply with an OK atom. Okay. So now let's handle the mark ready call. Okay. For this, we're updating the data as well. So mark player ready. And here, if both players are ready, we want to transition to countdown. So we need to check if both players are ready. And now, if both players are ready, we are going to change the state. Our next state is going to be called countdown. Let's put new data, and we're going to have some actions. If we want to have more than one action, we're doing it in a list. So let's first reply with an OK. Then, and the second action will be setting a timeout of this countdown state. So we're going to use the state timeout type of timeout, which is cancelled on a state change. So imagine if we add a new feature to our state machine, where user can do force countdown, which is force start, which just keeps this timeout. And then we want this timeout to be automatically cancelled. So yeah, let's make this feature possible without changes. So let's do state timeout. Then I have module attribute. It's set to 5 seconds. And the third tuple element is the code, the event data. So let's put it put there an atom countdown end. Okay, I think that's all for this. Now imagine that we want to handle the shoot events even when we're in countdown state. And that way that we want to postpone them and handle them when the game is started. So if a countdown state receives a shoot event, let's then just postpone it. So to do it, you do keep state and data, and the action element of this tuple is going to be just postpone. Now let's handle the timeout. So let's handle the countdown to game change. So def to handle the timeout, we're putting the first argument to, we're setting the first argument to state timeout, matching the first argument like that. The second argument is going to be matched to the event data, so countdown end, and of course data. And now, so we're changing the state. So next state, and as you can see, game is split into two substates. So let's decide that we want to have a state that looks like that. Game and player one. So our state is going to be a tuple. Obviously, we cannot do that when we're in state function mode, because since we want the handler function names to be called the same as states, state must be an atom. So let's actually change this to handler event function. But first, let's finish this one. So we're changing the state, we're putting the data, and we're going to do some actions. So we need to set two timeouts, like the small timeout, the round timeout that will jump here and there, and the timeout that will finish the whole game when no one finishes, when no one wins. So let's address the big timeout first. So to do a generic timeout, we do something like that. Then we're putting, yeah, so I set this to a minute. And event data, we can put whatever we want. Now let's tackle the small timeout, the round timeout. So to do so, we can just put a value here. So I set this to 20 seconds. Okay. I said we're going to change the callback mode to handle event function. It should be like that if we use state function. I forgot S here. Okay, and let's assume we got a new requirement that for every state change we need to send a message somewhere. So it might be a good idea to actually turn on the state enter mode as well. So we can do list here and first handle event function and state enter. First, let's handle the enter event. So okay, so enter, and the second argument is the old state, and the third argument is the current state, the new state. Yeah, so and okay, so let's log for the purpose of this talk, let's just log it. So, and let's not change anything there, so keep state and data. We can perform actions here as well, so we can, for example, set a timeout here, or stop the machine, or whatever. Okay, now let's change the remaining functions to the new handle event mode. The state is going to be a third argument. So here we're matching setup. Here we're matching setup. And let's do the same for countdown. So countdown. Okay, now let's handle the current state. Let's handle the shoot action, which will, if we don't miss, we take the opponent's ship down. So let's handle this call. And here we want to match that the permitted player is making this this action. Okay, so let's modify our data. And now, if a player wins a game, if a player takes the opponent's all the opponent's ships down, we want to transition to game end. Otherwise, we want to just change player's turn. So let's do if end game data. And if game ends, we're transitioning to next state. And so the next state is going to be end. We're passing the new data, and we're going to do two actions. So, of course, obviously, reply with an OK. And we have to cancel the game timeout. So when we change state here, this big timeout is not going to be cancelled automatically. And imagine that we're in a different state, and this state receives the state timeout of the game state. So it's not what we want. Let's cancel this timeout we launched. So you can do this like that. And else we're going to also to the next state, but it's going to be the other player turn. And all we're going to do is we're going to do two things: reply, and we need to set the timeout again. So we need to repeat it. Okay. Now let's handle all these timeouts. So let's handle the round timeout first. To do so, the event type is going to be timeout. Here is the value of this timeout, so we don't really care about it. The third argument is the game state, and the fourth argument is data. Okay, so let's change it to another state. So, and the only action we're going to do here is to repeat the round timeout. Then we need to handle the big timeout, so the game timeout. So let's do it. Event timeout game. This is our event data. We're going to transition to end state. So next state, and data, and we're not doing any actions here. Let's also handle a case where client calls generic state machine, but it doesn't have the function clause to handle it. So let's just keep state and data then. So keep state and data, and we'll reply with an error. Okay. Okay, so obviously I forgot about data. Okay, this looks good. Now let's say that when the game ends, we want to just stop the state machine. So one thing we could do is doing the internal event, which we can do like that. So next event, internal. And we could handle this like that. So internal, but let's not do it. Let's actually make use of the callback mode, because as you can see here we have like to end transitions, so we would have to put the event there and repeat ourselves. Here also you see that we have like put 3 times round timeout, whereas we could just do it in this enter event handler. So yeah, let's stop the state machine there. So if current state equals to end, let's just stop the machine with normal reason. Else. Okay, looks good. I hope it compiles, but if not, I have the working branch.
I think you forgot in the setup function. There is if and there is no else in setup.
Right, thank you. Okay, thank you. So if both players are ready, we are transitioning to a countdown. Otherwise, we're doing the same as here. Okay. Now fingers crossed. Nice. Let's for convenience do this, and let's launch our machine. Okay, it started, and as you can see, the enter event has logged a transition from setup to setup. This happened when you set the initial state, so our previous state is equal to the current state, actually. Okay, now let's place some ships. Place ship. Let's say A1. And for the other player, let's make it B2. Now let's make both players ready. So and player 2. As you can see, countdown has started, and we should expect that in 5 seconds. Yeah, it transitioned to the game, and it's player 1's turn. So it's a miss. Player 2. Let's end the game now. As you can see, game has ended. Let's see if the machine was stopped. Yep, it's stopped. Okay, now let's try with different settings to see if the postpone action is working correctly. So let's set countdown to 20 seconds so I can enter the event. And okay, let's leave it like that. Okay. Okay, and now do and we're waiting. I set it to 20 seconds. As you can see, after the state transition to player 1, the event was applied, and since player 1 won, the game is ended automatically. Now, one last run to see if game timeouts are working properly. So let's do it once again. Okay, so countdown. Then it should, yeah, it works. It doesn't work.
Yeah, you forgot the game state. You just pass the player 2, and you should pass the tuple player 2 and game and player 2 in timeout.
Okay, where is it? Timeout.
Handle event timeout 81 sphere, and in the tuple lower, when you get the other player, here you should pass.
Yeah, of course. Okay. Yeah, but let's assume it works. So it should be like that, of course. Live coding in a nutshell. Okay, that's all I had. I won't retry it because yeah, it works, I hope. So do you have any questions? Okay, then thank you. There are some cool resources, of course. Erlang documentation. There is also this article by Andrea Leopardi where he describes how he made a persistent connection manager with generic state machine. And there is also, if you wanted, GenState machine behavior for Elixir, when you can just put the countdown mode as a using macro options. So it's more idiomatic. I don't know if you prefer it. Okay, thank you.